Over the next few videos, I want to work through an example of some calculations with oblique shock waves. You'll recall the Drummond reflected shock tunnel from the video where we looked at sample results for attached and detached oblique shock waves. We did those tests at Mach 6.8. In our example here, we'll do our calculations at that Mach number. We'll look at the 3 shock inlet for the simple scramjet geometry that's the focus for this course. We'll consider a case where the first part of the inlet deflects this Mach 6.8 flow through an angle of 8 degrees, and when the second angle of the inlet is 10 degrees. We'll begin looking at this problem by specifying the geometry and then the flow conditions. So we'll start with the geometry. So our first surface is going to take the flow and it's going to deflect it through an angle of 8 degrees. Let me just try and make that a bit straighter. Our second surface is going to take the flow and deflect it through a further 10 degrees. Then we have our cowl, which is sitting up here somewhere, and that takes us through a third shock wave, which is going to deflect the flow through a combination of 10 degrees plus 8 degrees. We'll look at that a bit more in a moment. So let's put our shock waves in here. The first shock wave processes the oncoming flow, and that first shock wave strikes the edge of the cowl. The second shock wave strikes at the same location, and the third shock wave strikes at the entry to the combustor. Let's say that the flow is coming on at some Mach number, and we'll call that Mach 1, Mach number M1. And let's say that the flow condition is state 1 upstream of the first shock, it's state 2 downstream of the first shock, it's state 3 downstream of the second shock, and it's state 4 downstream of the third shock. And let's just label our shock waves. So we'll call this first one shock S1, the next one shock S2, and the third one shock S3. Let's just put a bit more geometry. So let's look at the capture area of this intake, or capture height. And we'll call that capture height H subscript C, C for capture. And then we'll say that the inlet takes the flow from that height HC and brings it down to height H3 in the combustor. Let's continue on by putting a little bit more geometry in here. So the first shock wave is generated by this first surface, which is at angle θ1 to the oncoming flow, and that generates this first shock wave, which we'll call β1. The second surface, let's just carry on the direction of the first surface. So that's the direction of the flow from the first surface. The second surface deflects the flow through an angle θ2 relative to the first, the flow angle behind the first shock wave, and that second shock wave is therefore going to be at an angle we'll call β2 to that oncoming flow direction for shock 2. Now I want to have a look back at that third shock wave. And to help us, let's just put a couple of streamlines in the flow. So let's say the oncoming flow is coming in this direction upstream of the first shock. The first surface deflects the flow to be parallel to that first surface, so in this direction here. The second surface deflects the flow to be parallel to that surface, so the flow gets deflected up there. And then our third shock wave is going to take us back such that our streamlines are parallel to the surfaces in the combustor and parallel to the oncoming flow. So let's just extend the direction of that flow direction behind the second shock wave. So it's going to be traveling in that direction parallel to this surface that caused the deflection. So the flow deflection angle that the flow has to go through generated by that third shock wave is going to be this angle here, which is going to be the sum of θ1 and θ2, because the first shock wave deflects the flow through θ1, the second shock wave through an additional θ2, the third shock wave has to turn it back parallel to the direction it was originally, so that third shock does a θ1 plus θ2 deflection, and therefore the shock angle in here is the one we're interested in, and we'll call that beta 3. The last bit of geometry I want to look at is just, oops, doing that, is what these heights here are. So the first surface has a vertical height associated with its length and its angle, and we'll call that h1. The second surface has some length and it's at some angle, we'll call that height h2. So that h1 plus h2 plus h3 is equal to the capture height hc. So we have our oncoming marker number m1 is equal to 6.8. We're going to say that our first angle of deflection of the surface θ1 is 8 degrees. Our second surface deflects the flow through a further 10 degrees, and let's give ourselves some capture height. Let's say that's a round number of 1 meter. Now if we specify the gas in terms of its ratio of specific heats, then these parameters here for this particular type of inlet completely specify the geometry. So we can calculate by going into the geometry what h1 is, and that turns out to be 0.3541 meters. h2 is equal to 0.5607 meters, and h3 is 0.0853 meters. I'm not going to go into the details here of how we calculate those numbers, but I will say that if we look at the geometry here, if we know what the length of this inlet surface, this first surface here is, and we know what the angle θ1 is, then we can determine what h1 is. Similarly, if we know the length of the second inlet surface, we can work out h2 from the length of that surface and θ1 and θ2. So this angle in here would be θ1. And then h3 is just going to be hc minus h1 plus h2. I want to just finish up formulating the problem by specifying the flow conditions. So let's say we've said that our oncoming Mach number is 6.8. We need some pressures and temperatures. We'll take conditions for around about 31 kilometers altitude in the Earth's atmosphere. Static pressure we'll set to a nice round number of 1 kilopascal, so 1000 pascals. We'll say that the static temperature at that altitude is around 220 Kelvin. And we'll say we've got air, so gamma is 1.4, and for air the gas constant R is 287 joules per kilogram Kelvin. So from those conditions we can calculate a few other parameters. So density of the flow, rho 1. Static density is the static pressure over the gas constant times the static temperature. And we put in those numbers, so we get 1000 over 287 times 220, and that comes out to be 0.01584 kilograms per meter cubed. We can also calculate the stagnation pressure of that flow using this expression here straight out of our isentropic flow analysis, and when we put the numbers in for that, we find that the stagnation pressure is 3.445 megapascals, so 3.445 by 10 to the 6 pascals. So with that, we've formulated our problem. We've got the geometry, we've got a sketch of the geometry, and we've got our notation that we're going to use. We've got what the flow conditions are oncoming to the flow, and so we'll stop here, and in the next video we'll pick up going through the analysis of the flow across the first shock wave.